Okay, we continue. Your point your roadmap to success. Okay.
Welcome to the 4.0 Roadmap Touchpoint for the DMD specialization.
You now have a 4.0 roadmap project and charter with objectives. You have thought about your mentor and have documented a self-assessment. Let's consider what you've learned about DMD thus far. In this specialization, you have heard from leadership who have described a business case for digital implementation. You've also heard from management, production, engineering, quality, and inspection personnel, to name a few. Most recently, you've heard how machining has been transformed from manual processes to intelligent machining. Now think about what you know about DMD and how you can make an impact in this field. What do you need to consider in order to get there? The National Institute of Standards and Technology, or NIST, estimates there are 600,000 advanced manufacturing jobs not filled. Your assignment is to document at least one future goal related to digital manufacturing and design paradigm, the steps required to achieve your goal or goals, and the obstacles you may have to overcome in order to achieve your objectives. We've put a few suggestions in the resource section to help you get started. Please begin to share your ideas with your family, peers, and mentors, along with using the discussion forum to capture your thoughts. This concludes this project lesson on guiding your future in digital manufacturing and design.
Okay. Kirill Isil Gold Mahara for visual application to be actually maybe good. Sharing again with the story. You can see demo. Password. Okay. Okay. Yeah, it might be good. We can see how we can see what is this. How can we see what is it? Then shot for image. Okay. And we can see something. We'll try the part file embedded software visual for the web. Okay. The file future state with improvement. You think about what you know about GMT and how you can effectively share all the image together. So, for visual digital manufacturing and design paradigm.
Paradigm.
Paradigm. Paradigm. Okay. Discussion. Share one or two potential risks that you identify in step 5 of your framework. What do you see at the basics of identify potential risks? Okay. Create a machine. For your final measure typical, you will be asked to develop point format or how you Generation mechanical from equal and static future relations study concept
Gleaned.
cleaned. Let's see what it is. Dun, 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 dun. Okay, where so okay, so we answer this one. One or two potential ways that you identify. How much is the sample shape? See benefit up. Get the potential which can be done. Then what do you see at benefit up? The benefit of identifying potential risk allow me to. How can this radical assist you in have me? Okay, can be done. Which is a successful check. From a set in roadmap can be done. I that maybe that I cannot find show. I can better prepare myself. Okay, this package help me to build my roadmap to success. Okay, let's see what this one you just GPT. Now what put the right answer? Okay. Okay. Take away. Below you will find number of key points for this course. Sensor is a device that detects and measures acoustic sensor for signal, while data aggregator component.
Data aggregator component.
aggregator component. Data processor, machine learning, project control, programmable logic control. Okay, yeah, I have the document to put to type. Material refer content college course. Okay, it's just the introduction. Then we have like the practical thing or something like that. Okay. Oh, then we go here. We need come back to answer to get 100 later. Now we finish this one already. So now industrial Internet of Things, introduction to Internet of Things, and embedded setup. Introduction. Maybe this one first. Okay. Objective define the term Internet of Things, stack the technological trend that have land define effect of Internet of Things. Okay. Survey. Yeah, survey we'll do it later if we have time. Let's see.
Welcome to Introduction to Programming the Internet of Things and Embedded Systems. I'm Professor Ian Harris. I'm a professor in the Department of Computer Science at the University of California, Irvine, in beautiful Irvine, California. I got my degree, my PhD from University of California, San Diego in 1997. Before that, I got my bachelor's at MIT in 1990. I do like computer security research. I do Internet of Things research, specifically building components, stuff that this course is about. And I also do work in testing and verification of hardware design.
Yes, I'm introduction. We have here course overview. Objective define, set, define, enumerate. Okay. Waiting per-reviewer assistant. Develop for module will include granted per-reviewer assistant. Squeeze. Quizzes. Okay. Yes, okay. Module 1. Objective. Okay. Fit in. Survey. Okay, if we need, we will see it later. Okay, just open it to see. Yes. I cannot open it. Don't know why, but yes. This one is the same.
And we'll be talking about Internet of Things.
Right.
Internet of Things is a pretty popular buzzword right now, but it's not one of those passing fads. Internet of Things is actually an important concept that's making changes to society right now. So welcome to Module 1, and we'll be talking about Internet of Things over the entire course, but in this module, we'll basically define the term. It's used in many different ways, depending on the speaker and their motivations and so on. We'll break down the term, talk about it, give some examples, so you get some kind of an intuitive understanding of what an Internet of Things device is and what it is not. Also, we'll talk about various trends, technology trends that lead to Internet of Things, that allow it, that enable it effectively, and make it all possible. And we'll talk a little bit about the impact on society of having things embedded everywhere that are watching you at all times and are networked. So we'll talk about that, privacy issues, and things like that. Thank you.
Okay. Okay. We see his laugh. Module.
So now it's a lab tour. This is my lab. Got a bunch of equipment here. Let's start off with these computers. These are sort of old and semi-defunct computers. These computers are actually for my computer security research. I actually have a group of students who want to look at attacking networks, look at attacking computer networks, and so I'm going to have them work on this. This will be a network, and they will attack it and try to defend it and see if they can do that. So that's what those are for. This is just a computer. Over here, we have some of the stuff that I use for hardware design. So I've got a soldering iron. Start with that. Soldering iron is used to solder together pieces of metal when we're building a system, and this is a cleaner for the iron. I've got my oscilloscope. Oscilloscope is a diagnostic tool. It's used to tell you the value of certain signals, certain waveforms. So if you want to see if the voltage of a signal over time, you connect this up, and this is the ground, and you can see the voltage of the signal over time on the screen. So I use that a lot. Got a multimeter. I use this even more. Multimeter is basically just a device, has two probes, and allows you to see the voltage, current, and resistance between the 2 points. So you can touch these two probes to different points in the circuit and see the voltage between them. Got a microscope. This is for working with small devices, so sometimes I'm looking at small printed circuit boards. Things are designed very compactly. So in order to desolder them and work with them properly, I need a magnifying glass or even better yet, this is actually better than a magnifying glass. It's got a light on it to give me good visualization of the component. Random parts, solder and snips and desoldering wick and so on. This is actually a mixed power supply and together, so controlled power supply multimeter. I don't use it too much, but it's very useful. This is just a crimping tool to crimp terminals onto the end of wires. This right here is a project I'm sort of working on still. Is a quadcopter, or a defunct quadcopter. It's got 4 motors, 4 actuators, 4 ESCs, electronic speed controllers. These control the speed of the motors. This is the control, the main flight controller for it. So this flight controller sends data to these ESCs to indicate what speed the motor should go at. This is the battery right here. This is maybe half the weight of the whole device. Then over here, I have my turntable, one of my turntables. So it's an old, dirty turntable, and it doesn't work right now. And since I have a lab, I feel like, why not fix it? I need to solder something together. Actually, this board.
If I hate lab, don't have it.
That needs to be resoldered. The board is decayed. And this is the turntable, the platter that goes on top of it once it's
just some
over here, I just have a box of
very old
a box of soldering irons and things like that. Tools that I use for my classes. So when I have a class and I wanted to solder, I just bring this whole box over to the class. And
not really research lab.
So over here, we have lots of different parts stacked up here. All kinds of different components, wires, cable, every wire and cable you could probably ever need. I have somewhere in here. Programs, microcontrollers, wire. These are my portable cases. So when I'm on the run to a class or something like that, I put stuff in this and carry it off. Duct tape is always good.
Not really.
What do I have? More equipment over here. Piles of resistors, all sizes and shapes and all that. Power supplies. Here we have Raspberry Pi. So we'll be seeing this in the class eventually. Let's take a look.
Raspberry Pi 2. Very old, I think.
That is a Raspberry Pi Model B. This is basically what we'll probably be working with. Maybe this is the right way. Yeah, this is right. The wording is right up this way. So this is Raspberry Pi, and we'll work with those. Also Arduinos. I got those too in my Arduino case. Over there. Here's one. It's not a brand new one, but they all look the same pretty much. That's an Arduino Uno. Actually, this is a shield for an Arduino. We'll talk about those too. It stacks. Notice it's the same size and configuration. You can stack it on top. This is an Ethernet shield, so this is an old Ethernet shield, but if you want to connect this to the Ethernet, you'll do that.
Okay.
And variety of components, and that's it. Thank you. The point of this lecture is really to just introduce the term Internet of Things, just to define the term, give you some kind of a general idea of what Internet of Things really is, what it's about. So we'll go through an example, a refrigerator example, and talk about how a refrigerator can be integrated into the Internet of Things, and how it's different than just a regular refrigerator. So let's break down the term, Internet of Things. We're probably going to start off with a thing of some kind. So in this case, we're talking about a refrigerator. And a refrigerator is just a thing. So it can be anything besides a computer, right? If it's a computer, we're not calling that a thing. But anything besides a computer, besides a traditional computer or laptop, desktop, server type of device, you'll call that a thing of some kind. And it has some features. It has some use. So in the case of a refrigerator like this, we know what a refrigerator does. It keeps things cold, so on. So you start off with a thing. Now, next thing you do is you add to that some type of computational intelligence. Usually that involves a processor, like what we're showing here. That's actually a picture of an Arduino, but it could be any type of computational intelligence. Typically, it's a microcontroller of some kind running some kind of code. So you see these devices all around your house, but it's the computer inside, right? So it doesn't look like a computer. It looks like a thing of some kind. It looks like a refrigerator, but it actually has computational intelligence inside. So it's really a computer hidden on the inside. And it somehow is used to improve the functionality of the device, to make the device do what it did before, but better. So that's what you start with. You start with a thing, you add some intelligence, some computer technology inside it. Now then, to top it off, you add internet connectivity. Now this is very common inside Internet of Things, and that's where the term Internet of Things comes from. You add some kind of internet connectivity. So now you got a thing. It's got some kind of computation inside, and it's got a network connection, which means it can use all sorts of other resources that are not local, right? Any kind of thing that it can reach on the internet is potentially accessible from this IoT device. So all that put together is generally what you would call an IoT device, an Internet of Things device. You take the thing, you put some intelligence in there, and you put some network connectivity. And remember that from the outside, this device doesn't look that much different than it used to look, right? It doesn't look like a computer. That's the main thing. It doesn't look like a computer. It doesn't have a full-on keyboard and a screen. It might have a screen and a few little buttons on it, but it doesn't look like a standard computer. You don't have to install Windows or iOS or whatever, or Android or whatever the operating system is. It's none of that complexity. So it's much simpler to use, just like the original thing was. So if you look at the new refrigerator, it's not going to be hard to use. You still open the door, close the door, plug it into the wall, that sort of thing. Get ice out of it. The same old simple interface. So traditional refrigerator. Keeps items cold, right? This is a non-Internet of Things. Keeps items cold, you put things in it, food, whatever it is. Real simple interface, right? But everybody knows how to use it. Decades ago, it was the same interface, right? 100 years ago, I don't know if I suppose there were refrigerators 100 years ago. 100 years ago, you had a refrigerator that looked basically the same thing. Now, an intelligent refrigerator, I'm using that term to mean a refrigerator that now has some kind of computational intelligence inside it. And you see a lot of this inside refrigerators nowadays. My fridge is like this. So, for instance, it'll warn you when the door's ajar. Usually it'll beep. Beep in some way, but it can talk to you if it wanted to. It doesn't matter. But it'll warn you that. So it basically has some sort of sensors built in that tell if the doors are shut. And if they're open for a certain amount of time, if they start a timer, if they're open for a certain amount of time, an alarm goes off, right? And that requires some kind of computational intelligence. It might tell you when the water filter needs replacing. Mine is annoying in that way. It tells me the same thing. So it starts beeping every time I try to get water now. In fact, right now I need a filter. So it just beeps and beeps and beeps every time I try to get water out of it, right? So again, it has some type of timer, keeps track of the date. Says, okay, this many days have gone by since you last refilled the filters and changed it. So again, requires computational intelligence. Note that it doesn't require networking yet, right? These tasks are just computational tasks. It could tell you when you're low on butter. Now, my fridge doesn't do this, but you can imagine a refrigerator that has some sort of sensor in there that can sense, maybe it has a camera in your butter tray, and it senses when your butter is low, right? Maybe it tests the weight of your butter, right? And if the weight is too low, it says, okay, there's butter in here, you are low on butter. It could easily warn you of that. And now mine doesn't do that. There are refrigerators that can do that sort of thing. But again, local intelligence is required, no real networking required to do that. It could also tell you when you buy foods that are high on fat content. Now, this, I've never actually seen such a refrigerator, but you could do this. You could take a picture, the fridge itself could have a camera inside, right? You could take a picture of the food that you ordered, look it up in some type of a library of food that it has, and look at the food content, look at the fat content and cholesterol and so on, and it can warn you, right? And it can do this with local data without network connectivity if you needed to. You can also have a set of recipes programmed into your refrigerator. I know there are refrigerators that have this. They can be programmed into your fridge, and it can suggest recipes for you based on the food that it sees inside. So you've got milk, you've got butter, you've got this, you've got that. You can make pancakes today, something like this. So that's another thing, another feature that you can add on to an intelligent refrigerator if you wanted to. And it requires a computational intelligence inside the refrigerator to do that. Also sensors, like cameras maybe, weight sensors, door sensors to see if the door's open and closed, something like that. And using all that together, you can enhance the properties of the refrigerator. So now this refrigerator, it does a lot more than what it used to do, but it's still very easy to use, right? You don't have to do anything complicated. It tells you, doors ajar, something like that. You don't have to, it's not going to work for you. No learning curve. Right? So that you might call that an intelligent refrigerator. But you'll notice that these features that I'm listing here, they don't require network connectivity in general. So these things that I'm listing here, they can do that with local sensors, right? That just sense and local processing that sense what's in your fridge and respond to you and give you information. So that's intelligent refrigerator, but maybe you wouldn't call that Internet of Things because it's not actually networked yet. So the ultimate, the IoT refrigerator. So the IoT refrigerator is basically the computational intelligence, but also network connectivity. So with the network connectivity, you can add another set of features on top of that you couldn't have added without the network connectivity. So for instance, you can have your refrigerator actually order food for you when the stock is low. That can easily happen. It can check. It can go straight to Amazon. Amazon, I guess I shouldn't advertise, but there are services from which you can go to supermarkets and order food, which I use one of these services, and they deliver food the next morning. Actually, it's pretty amazing. 7 in the morning, the food will be there on the doorstep. So you can have your fridge detect that you're low on butter, and then just order that, and then the next morning butter will appear on your doorstep. But that requires network connectivity. You have to be able to connect to the network and place the order, grab money out of your bank account, right? Transfer it to whoever you're purchasing from, things like that. Okay. You can search for low food prices. So it can also suggest to you, look, you might want to buy this item. You're low on butter. Buy butter from here rather than there because it's cheaper. And in fact, it can go ahead and just buy that, right? Or it can just suggest to you. But again, that requires network connectivity, right? We have to connect to the network, go search around different sites, different supermarket sites, find the different prices, compare them, and so on. It could order water filter when you need the water filter. So rather than annoying me and telling me you need water filter, beep, 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 it could just go and order that, and it could appear for me. UPS could deliver it the next day, right? So it could anticipate meals. It could be predictive. So it can know what kind of food you have in your fridge and order what you need for tomorrow's meals, right? So it can say, a good idea for food for you tomorrow is this type of meal that you've had in the past. I will order whatever you need for that meal, and then it'll appear on your doorstep the next morning, and then you'll have everything you need to cook what you need for the next day. It can search news prices. It can actually do more global type of searching. It can look at news prices to see what global trends are. So for instance, and this is elaborate, but you can certainly do this. It can look at news trends and say, oh, it's El Nino, right? The world's getting colder this year. That means that fruits are going to be more expensive, right? So I better stock up on fruits right now because I know that in a few months I won't be able to get them, right? Your machine could do that. Your fridge could do that. Now, I've never heard of a refrigerator that does that, but that is certainly possible if you have the computational intelligence inside the fridge and you have network connectivity so it can actually execute searches. It can also provide information to businesses to tell them what you're buying, right? Now, this maybe is not an advantage to you, but certainly, some store that's selling different types of foods, it might want to market to you, so they might want to know, oh, these people are buying this type of food a lot, so maybe we want to market to that type of food to them, right? So that's another thing that these devices do, and we'll talk a little bit more about that later. Thanks.
Yeah.
This lecture will give some more examples of Internet of Things devices, just to give you a sort of a better, more concrete idea of what these devices are and how they differ and how they're distinct from traditional computers. So we'll run through a few more examples and give a little bit more detail about their behaviors. So take a car. A car is an IoT device, I will claim. Okay. The reason I call it this is because if you look at a car, this is a thing clearly. If you look at a car, an old car, there's an old car, that's a 50s car maybe. So old cars had a certain interface, right? You have steering wheel, gas pedal, brakes, and so on, the radio, sort of simple, straightforward interface, what I would consider to be simple. Now that interface, it was basically implemented with electrical and mechanical controls, but there was no computational intelligence in there, right? Early cars, they didn't have computers in there, processors doing anything. There was electricity, there was mechanical stuff, but that was it. So that's an original device. It's not IoT from the 50s. But nowadays, cars have lots of computational intelligence. Let's take a look at this. So 21st century car. So what is that? Looks like a Prius, I think. This car, it's got lots of chips in it. So lots of processors. That car might have over 50 processors in it doing different tasks. For instance, it's got an anti-lock braking system. They all do these days. And the anti-lock braking system will have its own processor dedicated just to anti-lock braking. And so it's got that. It's got fuel injection, right? Fuel injection system. It's going to have another processor dedicated to that. So every subsystem has its own processor. And it's also got a stereo, say. Stereo system's got to have its own processor. But every subsystem inside the car has its own processor. But the thing about this car that you notice about this device is that even though it has its computational intelligence, it has the same basic interface as that 50s car. So you drive this car pretty much the same way. Now the 50s car, it probably had manual transmission, I'm going to guess, because it's the 50s. So this will have automatic transmission. But besides that, it has the same interface, the same steering wheel, gas pedal, brake. So you can train somebody to drive on the 50s car and they can drive this new car. Even though this new car is enhanced with all this computational intelligence. So that's the thing about IoT devices. They have a very simple interface. They want to be easy to use. They want to give you the benefit of this computational intelligence. So now you have anti-lock braking, for instance. Now, anti-lock braking, in case you don't know, anti-lock braking, it prevents the tires from locking. So you always want the tires to, you don't want the tires to skid compared to the road, right? They should always stay in good contact with the road. But if you brake hard, if you move fast, you brake hard, the car will skid and the tires will not move, but the car will move, right? So anti-lock braking tries to prevent that. Now, before anti-lock braking, what you used to do, I remember when I learned how to drive on snow, you skid a lot, right? So what you do is when you do a hard brake, you'll pump the brakes, right? Manually pump the brakes. Now, and you have to remember this. You have to be pretty consciously aware enough to remember to do this. Anti-lock braking do that for you, right? Anti-lock braking devices, they take care of that for you. So this is a great benefit to drivers nowadays. Kids don't even know about pumping brakes. They don't learn that because they don't have to. Anti-lock braking takes care of it. So the computational intelligence is helping you, relieving you of burdens that you didn't want to have to deal with. But the interface is beautiful. You don't have to worry. You just hit brake pedal just like you used to. It does better. It just does what you want it to do, does better, and makes everything easier for you. Now, a typical car, like this car that we're looking at right here, this car, it has computational intelligence. Now, whether or not it has networking is a different thing. These cars nowadays, actually, these days, cars are having more and more networking. And you may have heard of this in the news, but cars are networked, actually. So you can, for instance, remote start a car, right? Start it when you're not near the car. You can start it through the network. Cars also have to, what do they have in there? Those, I forget the name of the brand. There's OnStar is one brand name. But when there's an accident, the car can, through the internet, connect with 911 and call and get help, right? So this type of thing is present in cars. My car does not have that, but I'm cheap and I'm a professor. I buy old cars. So my cars are old, but new modern cars have these features built in there, and they are actually networked. So that would be a modern car, the most modern car, that would be an IoT device because it has the computational intelligence, and it's also networked to add extra flexibility. So that's one device. Let's take a look at another. Let's talk about logistics, tracking things, okay, logistics. So say you are Walmart or some big company, or you're the military, something like that, and you want to move lots of things between different places on a certain time scale, right? You need to get these from this manufacturing place to this sales place on this schedule. That's logistics. And the military is all about logistics, right? We are waging a war. We need to get these devices from here to here and these people from here to here on this time frame. So you want to move things. So say you're Walmart, and you would have to be able to track these devices that you're moving. You want to make sure they're moving from place to place in a certain time frame. And you want to be able to, at any time, be able to say, where is box number, whatever, right? How many boxes do we have of this type of device at this location at this time? And you need to be able to track that dynamically. So you can account for things like weather difficulties, right? Maybe the planes are shut down, so you can't move enough devices from here to here. So you need to know how many are here so you can reroute things. So to do that, one way, a very common way, is to use barcodes, right? This helps you because every box, every device, it has a barcode which has some basic information about what's in the box, right? And where the box came from, stuff like that, it's stuck on the box. Now barcodes are in very common use today, right? We use barcodes. If you look at any food item, you go to the supermarket, you check yourself out, you run the barcode over the scanner, right? So barcodes are very useful, and they have a certain amount of information on there, and they make it so that you can just scan the device and find out information about the device or whatever it is in the box, and it makes it easier to track. So this is basically old technology. Barcodes have been around for a long time. Nowadays, you also find RFID tags. So RFID tags, you can see the antenna for one right there. It's basically an electronic version of a barcode. And what you're seeing is that sort of spiraling wire. That's actually the antenna, okay, a remote antenna. And what RFID tags allow you to do, why they're an improvement over barcodes, the first thing is they basically have a processor inside there. So you can have a lot more information about the device than what you can code inside a barcode, right? A ton more information. And that information can change, right? Because barcode, once you print that on the box, that will never change, right? Until you rip off the barcode, put a new barcode on. But that data can never change. With an RFID tag, that thing can have flash memory in there if you want to, that actually reloads, that gets changed and updated over time. So for instance, if you want to track where a box moved, the box itself, its RFID tag can store that information over time. So as it moves from place to place, you can store that and you can see the whole path that the box took, right? So RFID tags, another benefit of these is that you don't have to be right next to them to scan them. So if you know anything about a barcode, you have to take a scanner, put it right up to the barcode in order to scan it. And you have to try, right? You have to, if you ever scan, like just yesterday, I was scanning food out, I have to work to get that scanner directly over my barcode, right? With RFID tags, there's a range. So you don't have to be within proximity. You don't have to have any particular orientation, just be near it, which is helpful, right? Then you can just run every box near a scanner and it'll catch it. So RFID tags have a lot of advantages over barcodes, and they can easily be networked. So the scanner can be networked, connected to the internet, so you keep constant track of where all your boxes are at some global site. So Walmart can know where every box is, in what manufacturer, what plant it's in, and they can keep it all centrally because the IoT RFID scanner is actually connected on the network to its main cloud service. So devices can become an IoT device if you put RFID tags and the computational intelligence onto them. Thank you. This lecture will compare IoT devices to standard computers, and we'll just compare and contrast, just so you get an idea of the difference between an IoT device and a computer, because they are substantially different, and we'll need to know this for later, because we're going to talk about how you design IoT devices, and the design methodologies are very different than what you use for a standard general-purpose computer. So IoT devices, one big difference between those type of devices and standard computers, say, and by standard computer I mean desktop, laptop, server, basically a big box with a keyboard, a big box, a little box with a keyboard and screen, mouse, that type of thing. So one difference is that IoT devices, the main function of an IoT device is not to compute, not to be a computer. Right? A computer, it is there to be a computer, to compute functions, right? To run programs. But an IoT device, that is not its main point. It has some other function besides that. So, for instance, we talked about cars last section, right? So cars, they're IoT devices. Their main function is not to compute anti-lock braking or to do fuel injection. Their main function, from the point of view of a user, is to be driven, right? To move you from place to place. And the computer is just to help that function, just to support that. Also, we talked about refrigerators, right, in an earlier lecture. So a refrigerator, it's a refrigerator. It keeps things cold. That's its main function. Now, computational intelligence can help you. Network connectivity can improve its ability, but that is not its main function to talk on the network. Its main function is not to run code, right? Even though it does that. Where a computer, its main function is to run code, right? So that's a big difference, is sort of the focus of the function. That IoT devices have this separate function, separate from computation. So computers, like I said, computers, their main function is to compute. They run code. Now, this code can do lots of different things, but they execute code. So, this picture right here, we're showing a decision-making process. It's sort of a high-level view of what a piece of code would look like. But there'll be conditions in there. If x is greater than 5, then perform this action. If x is less than 5, then do another action. Something like that. That's what code looks like, and that's the point of a computer, is to execute code, execute a sequence of functions in a particular order as determined by dynamic information, like that condition right there. That condition might check something dynamically at runtime. And we'll get into more detail of this because we will be coding in this class. But right now, the function of a computer, its main point is to run code like this. IoT devices, on the other hand, they don't. So computers are made to be general purpose, right? They're made to run any kind of code. So if you buy off the shelf, you buy some Intel processor. I see a Mac in front of me. Say I buy a Mac. This Mac is a laptop. This Mac laptop is meant to run code, and it can run any kind of code. I can play a video game on that thing. I can connect it up to a camera and video record something. I can do whatever kind of code I want to run on that computer. I can do that. So computers are made to be general purpose devices. Now, they're not particularly good or efficient at a particular application, but they are generally good at everything. So what that means is, say I take this one I see right here, this Mac. This Mac is now connected to this camera, right? And I'm assuming this Mac is probably running the PowerPoint slides that I'm presenting, and it's probably recording something, right? So sure, you can use a Mac to record video if you want to. You can connect up to camera, record a video, record a sequence. But a dedicated camera is better than a Mac at doing that, right? I can take a Mac and connect it to a webcam, and it's now a video recorder. But it's probably going to be better, more efficient to get a video camera that is made for that purpose to do that task. So computers are general purpose. They can do whatever you want. You hook something onto them, they can do what you want, but they are not necessarily the most efficient, most effective tool at doing that. So Internet of Things devices are generally special purpose things. So they are made to do a particular task or set of tasks that are all related to one thing. So as an example, music player, right? So I still own one of these, an MP3 player. You can buy them cheap. You can do it off a phone too, but I use a special purpose device, like an iPod, right? So these devices are made to play music. Now you can play music off a laptop, right? Desktop, whatever, but this device is made for music playing, and so it's more efficient. And by more efficient, I mean that its hardware and its software are designed just for that purpose. So if that's all you want to do, they play music very well. They're cheap, right? They don't cost much, right? You don't have to buy a whole laptop for that. You can just buy a little iPod, little tiny one, right? They have little iPods, the randomization shuffle, iPod shuffle, right? Tiny, cheap. Very compact, much smaller than a laptop, right? But they do their job. So that specific job, they do great. So these IoT devices are almost always special purpose devices. Take a car, right? Now, a car will do many different things, but they're all related to driving. So a car can do anti-lock braking. A car can do fuel injection, right? A car can do power steering, all these things. But they're all parts of one big task to drive, to be driven, right? So that's why I say a car does computation, but only computation that's related to the tasks that are driving tasks, right? So what that means is that the hardware and the software built in there are streamlined for that purpose. So that means they can be cheaper, more efficient in that way, cheaper and faster at doing just that one task. Now they wouldn't be suitable to do anything else, right? If you took your car and said, look, I want to play a video game in my car, you probably can't do that as well. But if you want to say, look, I want to do fuel injection in my car, hey, it's perfect for that, and it's great at that, and efficient at that. So that's a big difference between IoT devices and general purpose computers. IoT devices are special purpose, they do a particular thing.
Yes, so we finish today. I think the order we finish in the next one, and then we finish all. Now it's kind of introduction, introduction. Not very high, yes. Sound not very interesting to me. Okay.